Welcome to Biomaterials. What are we going to talk about today? Today we're going to talk about natural proteins. And in particular we're going to talk about two natural proteins, elastin and collagen, and how they can, what are connections between their microstructure and macroscopic properties that we observe in them, and what are some engineering uses for these materials. So first we'll talk about elastin. And elastin, we'll talk about sort of two phenomena that elastin sort of exhibits, or we can discuss in the context of elastin. One is basically hydrophilic and hydrophobic regions, and elastin on the amino acid chain. Right, so proteins are made up of amino acids. We'll talk about hydrophilic and hydrophobic regions on the polypeptides, and basically how this relates to things like coiling and strain. That elastin can exhibit before it fails. And then also we'll talk about elastin, and we'll sort of look at some of the chemistry of some of the amino acids that make up elastin, and we'll talk about sites for cross-linking. After we're done talking about elastin, we'll talk about collagen. And when we talk about collagen, we'll talk about regularity in the sequence of amino acids, and as well as chirality of the carbon and when we talk about and basically both of these will sort of have implications for the mechanical macroscopic mechanical properties. Of collagen. So, the idea is pretty similar for both of these, right? We're going to draw connections between what's happening at the atomic scale in terms of hydrophilic or hydrophobic regions on polypeptides and macroscopically observable mechanical properties, for example, how stretchy elastin can be. And we'll also talk about things that are happening at the atomic scale for collagen, and sort of how sort of very structural things down at the atomic level can give rise to some of the phenomenal properties that we can observe macroscopically for collagen, and then also we'll sort of finish off our discussion of collagen with a brief discussion of some applications, or I guess one important application for collagen. So first, let's start off by talking about elastin. So what is elastin? It's a sequence of amino acids, aka a polypeptide, or you might call it a protein. You might call it a sequence of amino acids. Right, a rose by any other name would smell as sweet, right? So elastin, it has a whole bunch of names. And where do you find elastin? It's a structural component in a lot of soft tissues. So soft tissue, structural component. And in particular, where one region in our bodies where we find lots of elastin is in skin. So for example, in skin. So So elastin is basically one of the molecules that is responsible for our skin being as stretchy as it is, right? If we think about it, skin needs to fit over weird shapes. Our joints bend a lot, right? If we think about the tissue that sort of goes over the knuckle in my joint, it goes from having a length of, maybe 1 centimeter to, once I've bent my joint, having a length of like 2 or more centimeters, right? So, I mean, if you think about it, just my knuckle bending, the skin that sort of goes over that knuckle experiences incredible amounts of strain. And elastin can support that strain without breaking, due to what's happening down at the molecular level. So a key thing is here, it supports large strains without breaking. Except, I guess, in the winter when your hands get really cold and your skin gets brittle and chaps and cracks and all that stuff, which is why we use moisturizer. But anyway, back to this idea of elastin. Down at the molecular level, elastin can support large strains without breaking. And the key thing, so it can support large strains without breaking, but yet it can do another thing, in that it can support loads indefinitely. Too, right? It's not like I don't have my skin, on my body, and then I go to bed and wake up in the morning and like all my skin has sort of sloughed off, right? Like it stays there, right? Even though like, the weight of the tissues and the pressure of my blood and all that stuff is sort of constantly trying to deform and press away this elastin. The elastin it stays there. It keeps everything in place. So it can simultaneously support loads indefinitely, but also support incredible amounts of strain when I am deforming. So it's truly a remarkable molecule in there. It's made up of mostly 3 amino acids. And also to sketch them, I'll sketch them down here. So lysine, glycine, and proline. What does lysine look like? So remember, amino acids have a carboxylic acid group right here, and they also have an amine group. So there's an NH2. Lysine is kind of cool in that it has actually sort of extra chain NH2 over here. So lysine basically has 2 of these amino acids. Glycine is the simplest of all amino acids, in that all it has is its amine group and its carboxylic acid group, and this carbon right here basically has 2 hydrogens, that I haven't drawn here. And then proline is a little bit interesting in that it doesn't have exactly an amine group, but rather it has an NH that's part of this kind of weird carbon ring. So that's these molecular structures right here. So take a moment now. Let's work backwards. Let's work backwards in these things right here. Thinking about supporting loads indefinitely, pause and ponder which of these 3 is responsible for that, for this property of being able to support loads indefinitely. Well, hopefully you've had a chance to pause and ponder which of the 3 is responsible for supporting loads indefinitely. Well, if you remember back to the lectures on viscoelasticity, creep, and things like that, being able to support loads indefinitely, we basically need crosslinking. And it turns out that this cross-linking can basically be accomplished by this extra amine group right here. So this is basically a site for cross-linking. And what does that mean? Basically, we can have this amino acid and carboxylic acid, this amine group in carboxylic acid forming a chain, but there are periodic NH2s sticking out of those chains, and those NH2s can bind with carboxylic acids of adjacent chains. So basically, this site can be for cross-linking, and these can bond with carboxylic acid in adjacent chains. Isn't that awesome? So basically, it has sort of built-in sites where we can cross-link to other chains. And, you know, it might be the actual elastin itself in another chain that it bonds to, right? Like it exposed COOH on the end of another chain. It's mostly 3 amino acids, so there might be some other amino acids that have a COOH group sticking off the side that then this can bond to. So it can bond with adjacent chains, and via enzymes in our bodies, this link can be the link can be covalent. Which is awesome, right? So that's basically what, you know, those covalent cross links, basically what means I can pull this skin a bit, but, you know, and I keep pulling it, it's not like my skin just keeps stretching out and stretching out and stretching out. And that's, you know, what helps me stay the shape that I am, which is great. So these bonds can be covalent. It turns out that if you want to do histology, so for example, if you want to like take a tumor out of a patient and then look at that tumor under the microscope, or if you want to, you know, do animal studies to sort of explore like what's happening with various implants or things like that, in histology, basically the first step is called tissue fixation. And tissue fixation basically means that you cross-link everything to everything else. So, you know, so what does that look like? Well, you basically put in a molecule that cross-links all the things. So, you know, so what does that look like? Well, looks like this. Again, sorry for the memes. My memes are mostly 2010 era, but yeah, this is supposed to be the cross-link, the something all the things mean. So you basically put in a molecule that basically binds NH2 groups to all NH2 groups. So one particular molecule that can cross-link all the things is glutaraldehyde, which is a molecule that looks like this. Again, that's not a COOH group on either side, but just an aldehyde group on each side. And basically what this does is each of these sites right here react to form a permanent covalent bond with an amine group. So these react to form covalent bond with amine, with an NH2. I'll leave out the exact details of the chemistry, but basically what happens is if you have two of these, there in our elastin, there are so many exposed NH2 groups that basically this glutaraldehyde comes in and cross-links all of the elastin chains to all of the other elastin chains, locking everything in place. And when you're doing histology or tissue fixation, you basically want everything locked in place such that when you slice it in thin sections and look at it at the microscope slide, the tissue structures haven't degraded since since you took that tumor out of the patient to look at it. So basically this fixation is something, I mean, obviously it kills everything in the tissue, but it basically holds all of those structures in place until the technician can basically look at it under the microscope right there. So glutaraldehyde is basically something that cross-links all the things to all the things. Our body takes a more subtle approach where it enzymatically cross-links some, but not all of the lysines to things on adjacent chains. So there we have it here. Let's now talk a little bit about how these molecules could potentially support large strains without breaking. Well, it turns out that supporting large strains without breaking basically requires lots of coiling. Right? If we think about it, if there's some crosslink here and some crosslink here, we basically need lots of coiling between those crosslinks such that when we go to stretch it out, there's plenty of room to sort of just uncoil these chains before we sort of have sort of stretched them, uncoiled it to the max, and now we're actually tugging on the covalent bonds rather than uncoiling. So we basically need lots of uncoiling, which basically means lots of strain until pulling on covalent bonds. So what's this uncoil? How do we get sort of coiling structure like this? Well, it turns out that we basically have hydrophilic regions and hydrophobic regions within these molecules right here. So pause and ponder. What sites on these amino acids and what sites might be hydrophilic? What ones might be hydrophobic? Well, the key thing here is regions that sort of have large places with just hydrogen carbon and carbon bonds. These regions are basically going to be hydrophobic. And what do? They basically pull themselves, these sort of collapse in on themselves. So different chains of elastin will basically rotate and contort themselves such that they tuck all the hydrophobic regions together away from the water in the surrounding tissue. And so they basically tuck or coil. They tuck or coil away from water, and this, but it's a relatively weak process that you can undo with some mechanical force. So basically, this tucking and coiling effect gives the tissue, gives the elastin sort of some natural state that's kind of condensed like this. But when I go to stretch my finger, I can uncoil all of those sort of tucked away hydrophobic regions. They don't want to interact with the water, but they do if I stretch them. They will if I stretch them out a little bit. And then once I've released that load, then they sort of want to tuck themselves back together to avoid water. So they tuck and coil away from water. Force pulls apart. And then they basically recoil when force is removed. And that's basically the nature by which collagen, by which elastin can sort of have a lot of stretchiness, but also support loads indefinitely from the crosslinks. So this concludes our discussion of elastin and how there's some amount of natural crosslinking. We can basically lock everything in place with fixants, and there's sort of this coiling and uncoiling process dominated by the hydrophobic regions of this. So now let's talk a little bit about collagen. Collagen has 3 amino acids. It's a 3 amino acid sequence that repeats. So what are the 3 amino acids that make up collagen? Well, the first one is glycine. And then it's called like X, Y. And basically this repeats. And the the Y that makes up glycine is usually hydroxyproline. So let's sketch what those let's sketch what those amino acids look like. If you remember, glycine was the simplest of amino acids. So glycine was NH2 and a COOH. So NH2, a carbon with 2 hydrogens, and then a COOH right here. X can be variable, right? It's not always the same thing, and there are different types of collagen, at least 10 or 11 different types of collagen in our bodies and in other mammals. So, exactly what type of collagen depends on sort of what this X is. But hydroxyproline looks like this, looks similar to proline, right? So this is proline. Hydroxyproline is basically just proline, but with an extra OH group. So we have an NH. We have this carbon ring that looks like this, and then there's this COOH right here. So it's this is proline right here, but hydroxyproline just has an OH group like this. So what's an interesting thing about collagen? Collagen is usually stiffer and stronger than elastin. So stiffer and stronger than elastin. So what gives collagen its stiffness and strength? Well, its stiffness and strength comes from this idea that this sequence, this glycine XY, glycine XY, glycine XY repeats over and over and over again. So this basically repeats, and through its repetition, it forms a helix, and then 3 helices bind together to form a triple helix. So through repetition, forms helix, and 3 bind together to form a triple helix. And then these triple helices can then form bundles, and then those bundles or fibrils, and these fibrils can form fibers, and these fibers can form bundles, and you basically get this kind of hierarchical structure of things here. But basically, at its very base, it sort of has this triple helix. Now, why might collagen do this? Well, basically, if you pack together all of these molecules in a triple helix, then it becomes very much more difficult than elastin to form them. So elastin kind of had this sort of like random coiling where we could sort of stretch it out by unpacking it. Collagen locks itself into this triple helix, and it ends up being a lot stiffer. So basically, if it's locked into a triple helix, that makes it stiffer. That's basically what gives it its stiffness. Now you might ask, like, how might a structure repeating over and over and over again form a triple helix? Well, the connection between repetition and helical, the connection between a repetition and a helix, this basically has to do with the connection between a repetition and a helix has to do with the chirality of carbon. So here, imagine these reds that I have right here are sort of the red that would kind of make up like this molecule, or this carbon right here. So carbon likes to bond to four things. So here I have these red blobs bonded to four neighbors: yellow, green, pink, and blue. And if you'll notice, these are actually these are different from one another. So even though they're made up of sort of the same things, even though the carbon is bonded to the same four things, you can basically say, hey, all right, I'll take this carbon, I'll put pink on top, and then I'll sort of line up the blues pointing in this direction. And here you sort of see, these are flip-flopped, right? So there's no way to get to rotate this one to get it to look exactly like this one. You can say, okay, well, all right, now I'm gonna line up, I'll still keep pink on top, and now I want to line up the green. So if I keep pink on top and have green to the right, now the blue and yellow are flip-flopped. So there's no way to get through rotations to essentially get these to be the same as each other. You're always going to have something flip-flopped in a weird way. So how does this idea impact collagen? Our body uses only one type of amino acids, so it uses only the L type. So basically, here's our carbon. Our bodies use only L type. And actually, most organisms on Earth only use the L type, and that's basically saying, hey, we've only used one. We don't actually ever use this. And if we sort of use the same one every time we get a glycine XY, we're sort of building. We're incrementing our sort of tetrahedrons, and this tetrahedron sort of results in some kind of bending each time we add an amino acid. So by always using the L type, and by having a structure that repeats over and over again, you can imagine incrementing it sort of like a staircase that basically builds up and builds up and builds up, and every amino acid that we build, provided it's always this L type, adds an increment to the thing. So a combination between chirality, the 3D-ness of carbon, and always using the L type as opposed to the D type, and having this repetitive structure, just spontaneously these collagen chains form triple helices. And based on the X and the Y and all that stuff, just the spacing of all of the bonds and the sizes of all the molecules, they spontaneously snap together to form a triple helix. And the triple helix is sort of the formation of a triple helix is kind of due to also this hydrophobic effect, where basically the glycine, all the parts of the glycine, the hydrophobic parts of the glycine and the smaller hydrophobic parts of the hydroxyproline, they sort of try to tuck themselves together. So that's basically why collagen ends up the way it does. So now let's talk about an application of collagen. Well, collagen is one of the main structural components. So collagen is basically the main structural component in tendons and ligaments. In tendons, ligaments, cartilage, etc. It also appears in bone too. I know bone is mostly mineral, but there are these collagen fibers that permeate the bone, locking all of those crystals together. We talked about that briefly in the lecture on composites and how amazing bone is. it turns out that so there are lots of tissue engineering uses, right? People trying to create collagen 3D printed or injection molded, or other formations of collagen gels for tissue engineering. You might have had experience with collagen in your everyday life. There's a soluble form. There's a soluble form of collagen called gelatin. It's yummy, and it can be used to create gels. So here I have some gummies that I give my kids. And if you look at the ingredients list, the third ingredient, I guess the fourth ingredient, there's some sugar and water, which, but the fourth ingredient right here is to basically give these gummies their gelled structure is gelatin right here, and that's basically the soluble form of collagen. So you can have collagen creating things as strong as tendons and ligaments. You can also create sort of a very more dilute and solubilized form of collagen that sort of creates gummy gels, which can create a pleasant sensation for candies and gums and things like that. So for anyone who's vegetarian, you better watch out, because a lot of candies, in particular a lot of gummy candies, contain gelatin, which is actually derived from collagen, and most collagen that's used in the production of these gummies is animal sourced. So yeah, better watch out, vegetarians. They hide meat in everything. Not all of it ethically sourced, so better watch out. But of course, gelatin has use in bioengineering, beyond just getting kids to take their vitamins. One of the coolest uses of collagen is in these gel foam plugs. So collagen can basically be used to form gel foam plugs. And what's the cool thing about collagen? Well, basically our body naturally has enzymes that can break collagen down, right? If our bodies didn't, then we would create a bunch of collagen and then have no way to break it down. No, of course. So evolution has gifted us with the ability to dissolve collagen, not immediately, but eventually. So basically, you can create gelatin, these gelatin foam plugs that biodegrade in a predictable way. And in particular, these gel foam plugs have actually saved women's lives. So during labor, you can have, here's the uterus, right? So let's say a woman is giving labor, baby comes out, there's the placenta, which is also supposed to come out after the baby comes out. So baby's already come out, time for placenta to come out, but the placenta basically is highly vascular. It's highly vascular. So basically, between the uterine wall and the placenta, that's how mom and baby were able to exchange nutrients and waste during pregnancy. Baby came out, we don't need the placenta anymore. But all of these vascular connections are supposed to sort of, break themselves off as the placenta comes out. Those vascular connections are not always properly terminated. So not properly terminated. So if they're not properly terminated, it results in something called placenta accreta, and basically where some of the placenta comes out, but this highly vascular tissue remains, and this can cause patients to basically hemorrhage, where essentially you have this highly vascular region with a ton of blood pumping through. The placenta was supposed to kind of package itself up nicely and come out during pregnancy, or during birth, or immediately after birth, but it didn't. it basically left this hilar vascular region open, which can result in tons of bleeding. And if this happened, let's say 100 years ago, mom would die due to all of the blood loss. If this happened 50 years ago, their solution would be to take out the whole uterus, and then, that's the end of it. No more, that's a risky surgery. And then also, obviously mom can't have any additional babies after that, so that kind of puts the end to the family that this couple wanted to, would want to develop. And if you had this happen, 20 years ago, they would basically send in some implements and try to sort of clean out as much of the placenta tissue as possible. They would sort of implant this bulb that the uterus would be contracting on, and try to sort of apply and that contraction would sort of apply some pressure to the highly vascular region, and that sort of applied pressure would try to stop as much blood flow as possible. But even then, that's still a painful process. The recovery is not always complete. Oftentimes it leaves sort of scar tissue remaining in the uterus, and that can make getting pregnant another time, a second time for future babies, that can make that very difficult, and that can also lead to second hemorrhages, if the placenta, is sort of still left in there. So what do we do in the 21st century? Well, in the 21st century, you can imagine some blood vessels. There are, let's say, lots of blood vessels that go around. There might be some blood vessels that feed this region and other blood vessels that don't. So what they can do is they basically inject the patient with a radio opaque dye. So they basically do a radio opaque dye, and that basically stains all of the blood vessels inside the patient and makes it show up on like a video CT scan. So these are vessels. And these blood vessels, then show up, and the physicians can see. And then the physicians can see where, what blood vessels are feeding the hemorrhage within the uterus. And then what they do is they stick in a catheter, and they thread that catheter right to the point where the accreta is, or just upstream of where the accreta is, of where the hemorrhage is, and they insert a gelatin plug. And this plug is properly formulated from a chemical standpoint to be sort of be porous enough to let in just a little bit of blood flow, so you don't starve all of the tissues downstream, but it blocks most of the blood flow to that one hemorrhage in the placenta. So allows a little bit of blood flow, but blocks most flow to the hemorrhage. So it blocks most of the blood flow. And then basically once most of the blood flow is blocked to this remaining piece of a placenta, it basically shrivels up and falls out after that, leaving the uterus back, restored to its healthy state. And of course the catheter can be removed and the radio-opaque dye is cleared from the system. And then eventually, once that remaining piece of vascular placenta has sort of shriveled up and properly detached and left, then the gelatin plug dissolves after. So it dissolves later, because our body has enzymes that sort of naturally are looking to sort of break down some of these tissues. So what's the key takeaway here? Awesome biomaterials in conjunction with other medical devices like catheters, radio-opaque dyes, and CT imaging can basically allow patients who have had what would have been a very life-threatening condition to be fully restored to their original uterine health after that. So thank goodness we're in the 21st century. So thanks again for watching. Hopefully you've been inspired and excited about a lot of natural proteins, and you're able to draw some connections between what's happening at the molecular level and what are some macroscopic properties that we observe in terms of the strength and the stiffness and the stress-strain relationships of these natural polymers. Thanks again for watching, and good luck with your study of biomaterials.